Chapter 5, One-Dimensional Unsteady Conduction. We start with Topic 1, Basic Concept. A. What is one-dimensional or 1D conduction? In previous chapters 1 and 3, we have been focusing upon 1D conduction. For example, in this rectangular plate, due to the temperature difference in the x direction, there's a conduction heat flow in that direction as well. Therefore, we see this is a one-dimensional conduction. On the other hand, in this long rectangular bar, not only do we have a temperature difference and then a conduction heat flow in the x direction, but also the temperature difference and then conduction heat flow in the y direction. Therefore, we see this is a two-dimensional conduction. Now, we can define one-dimensional conduction, which is conduction heat transfer is more significant in one direction than in other directions. B. What is unsteady or transient conduction? In the past, we studied steady state conduction, which is a heat transfer process during which the temperature and the heat rate do not change over time. Contrarily, unsteady conduction is a heat transfer process during which all the heat transfer variables vary with both time and location. For example, the temperature at the left surface of wall, initially it is at 30 degrees. Over time, it is decreasing. So this is a unsteady conduction. Then we would ask, what causes a steady conduction process to become transient? The answer is whenever there's a sudden change on the system boundary conditions or on the internal conditions, a steady process can become an unsteady one. For example, this copper initially at 50 degrees is suddenly quenching in a cold water at 0 degrees. Originally, it is steady conduction. All of a sudden, it becomes unsteady because the temperature changes over time. C. What is unsteady conduction system? It is that a solid body could be a long plain wall, could be a long solid cylinder, could be a solid sphere, is suddenly subject to convection with the temperature T infinity and heat transfer coefficient H. Initially, the temperature is at Ti, so Ti represents the initial temperature of the body. Usually, the initial temperature within the body is uniform. In order to visualize the initial temperature of the body, we simply use a straight line to represent it. Finally, we introduce the characteristic length LC to represent the important dimension that is used to define the scale of a physical system. The characteristic length is just like the outstanding personality to describe a person. The characteristic length LC mathematically defined as volume of the body divided by the surface area. For example, for the sphere body, this is the volume, this is the surface area, so the LC is 1/3 of a radius. Similarly, the characteristic length LC for long solid cylinder is half of the radius. Finally, the characteristic length for a long plane wall is half of the thickness. At this point, you're thinking to yourself, one-dimensional unsteady conduction is complicated. Not only does it depend upon location, but also it relies on time. The process is described mathematically by partial differential equation. You wonder, there's any way we can simplify the calculation? The answer is yes. Now we move on to topic 2, lumped heat capacity system. What is it? A lumped system is such a system that the interior temperature of some bodies remains essentially uniform in space at all times during a heat transfer process. For example, a small copper ball is placed into an oven at 200 degrees. Initially, the copper at 20 degrees. 5 seconds later, the copper temperature becomes 50 degrees, and at each point, they're close to this value. At another 5 seconds, the temperature of the copper ball rises to 70 degrees. At each point, the temperature is close to 70. So essentially, it is uniform. Therefore, the small copper ball can be modeled as a lumped system. On the contrary, the beef is placed in the same oven even after 2 hours. The roast beef temperature is not uniform within the body, in the space. Therefore, a roast beef cannot be modeled as a lumped system. Then you see, what is the heat transfer implication for a lumped heat capacity system? The implication is that the temperature and the energy stored will be only the function of a time. B, what is the math equation for temperature and energy stored for such a lumped system that it has density, specific heat, thermal conductivity, and volume, and the characteristic lengths LC. The initial temperature of the body is uniform at Ti, and suddenly is subject to convection with fluid at temperature T infinity and heat transfer coefficient H. Equation 1 represents half the temperature changes with time, where this tau T is a thermal time constant. Equation 2 defines the tau T thermal time constant in the unit second. It is a combination of heat transfer variables. Equation 3 represents the stored energy Q have a change with time. In this equation, Q maximum is the maximum energy that can be stored within the body. Equation 4 defines the Q maximum. There's an analogy between maximum energy stored Q max with volume. The empty cup volume represents the energy rho V CPTI. This already filled volume represents the energy rho V CP T infinity. And the difference between these two is this empty volume representing the Q max. Now we can apply all the knowledge equation we learned to do example 5-1. A thermal junction approximated as a sphere. Initially, it is at Ti. It has thermal conductivity, specific heat, and the density with the diameter d, which is unknown. Suddenly, the junction is placed in a gas stream at the temperature T infinity and heat transfer coefficient H. This heat transfer process has a time constant of tau T, 1 second. That's what we know. According to the hint, initial temperature plus suddenly change, we can confirm it is an unsteady conduction. Since the geometry is a sphere, immediately we can get the definition for the characteristic length LC, which is 1/3 of a radius or 1/6 of diameter. What we're looking for then? A. Determine the diameter needed for the thermocouple junction. B. How long will it take for the junction to reach 199? Meaning, how long it takes for the junction to change from 25 to 199 after it suddenly exposed to the 200 gas stream? C. How long will it take for the junction to reach 75% maximum energy stored in the sphere? You have seen this analogy. This represents the initial temperature, this represents the occupied temperature, and the difference is the maximum energy can be stored. In the beginning, it is stored energy is 0. After some time, 75% energy is stored. How long it takes, that's what we need to find out. Step 2. The solution strategy. Once we know it is unsteady conduction, we assume it is a lumped heat capacity system, so that we can select the proper equation. We select equation 1 because we know the time constant tau T, and it relates to diameter unknown. We select equation 2 because it related to the temperature 199 with time, which need to be found. We select equation 3, which is a little bit math rearrangement from the original equation. Since we know the percentage 75%, it relates to the time need to be found. Next, we simply plug into numbers into those equations. Tau density, specific heat, diameter unknown, heat transfer coefficient, solve for D. It is a small number. B. We know the temperature 199 to be reached. This is the moving fluid, the gas stream temperature, initial temperature, the gas flow temperature, and this exponential time we need to find out. This is a time constant tau T. We need to do the natural log on both sides, then solve for T. Is a short time. C. We plug into number with 75%, 1 minus exponential time needs to be found, time constant, rearrange, then do the natural log, solve for T. It is even shorter. Step 5, we assume it is a lumped system. Now we need to verify. We introduce a variable called Bi, defined as H, heat transfer coefficient, time characteristic length, LC, over thermoconductivity, K. We get a really small value. We see this is less than this criterion, and it confirmed that it is lumped system. Next, we really need to answer the question under what condition a system is lumped. We introduce a Biot number. Mathematically, it's defined as heat transfer coefficient H times the characteristic length divided by the thermoconductivity of the solid body. There is no unit for the Biot number. Then the justification is that if the Biot number value is less than 0.1, then the system is lumped. As a result, you can apply all the equations we introduced for the temperature and the stored energy, how they change over time. However, what exactly if the Biot number less than 1, the system is lumped? Let's do the math rearrangement first. So this is the definition for the Biot number. We do this rearranged out C over K divided 1 over H. Then time the surface area 1 over A on the numerator and the denominator. So this look like to me is the thermal resistance for the conduction. 1 over HA is the thermal resistance for the convection. So for such a system, the solid body subject to convection with thermal circuit is still does not clearly show why the Biot number is small than the system is lumped. Let's look at another image. Let's see. If the Biot number is small, much than less 1, so the resistance is small between these two temperatures, then the difference in these two temperatures will be small. For example, this temperature, surface temperature is 101, this surface temperature is 100. The difference between these two is only 1 degree. On the other hand, if the Biot number is small, the resistance for the convection is large, so the temperature difference between these two will be large. For example, as the surface temperature is 100, the fluid temperature is 10, so difference is 90 degrees. If we compare, 1 degree is much less than 90 degrees. Indicate that if a Biot number is really small, the temperature difference at each point from each other would be small, indicating that the interior temperature of the body is almost uniform. That's exactly the lumped system definition. Finally, if the Biot number is greater than 0.1, then the system is not lumped, just like the roasted beef inside the oven. So we need to use different equations to do the calculation, and the temperature will depend upon both location and the time. At this point, we finished chapter 5. We introduced a new concept and new variables and new equations. The goal is for you to be able to apply those equation steps to solve unsteady conduction. This is a beautiful summary and outcomes about a concept, variables, scales, equations. Then we end of chapter 5.